Hello. Thank you for coming today. My name is Antonio Torralba. I'm a professor of electrical engineering and computer science at MIT, and I'm also the director of the MIT IBM Watson AI Lab, which is an amazing example of fruitful collaboration between academy and industry. And I'm also the director of the MIT Quest for Intelligence. The Quest for Intelligence is an MIT-wide effort trying to understand what is intelligence and answer fundamental questions about human and machine intelligence. My job now is to introduce the next three speakers, Tenenbaum, Dimitris Bertsimas, and Aleksander Mądry. All of them are my colleagues, and they are very involved with the Quest for Intelligence. And they are all superstars in their own areas of research, working with amazing students. So please join me in welcoming to the stage Tenenbaum.
All right. So I want to ask this question. Why do we have today all these AI technologies, but no real AI? So what I mean is, we have machines that do things we used to think only humans could do, but we don't have anything like the flexible, general-purpose intelligence that each of you can use to do every one of these things for yourself. So why not? What's the gap? Well, the neural networks and deep learning driving today's AI are based on simple equations that were derived in the 1970s and 1980s to capture the most basic animal learning processes. Think Pavlov's dogs, or a rat in a maze. They're finding associations, recognizing patterns, but not understanding. And that means they're at most one small step towards real machine intelligence. Real intelligence is not just recognizing patterns, but modeling the world, explaining and understanding what you see, imagining things that you could see but haven't seen yet, solving problems, making plans to make those things real, and then building new models as you learn more about the world. Now, the goal of my work is to try to write down these kinds of equations, to capture this kind of human learning, all right? And then to use this to build more human-like forms of AI. And I'm starting with trying to understand how children learn and think, because they're the original model builders. And we are still far from having AI with the intelligence of even a 1.5-year-old. But imagine if we could get there. Imagine if we could build a machine that grows into intelligence the way a person does, that starts like a baby and learns like a child. This may not be our only route to real AI, but it could be our best bet. Because think about it, a human child is the only known scaling route in the universe. It's the only system we know that reliably, demonstrably grows into human intelligence, starting from much less. And we know that even small steps towards this could be big. So we're starting with the most basic common sense that's in every 1.5-year-old, but no AI. The intuitive physics that you see in a child like this one, stacking up blocks, playing with toys. Or the intuitive psychology that you see in a kid like this one here, another 1.5-year-old, that lets them figure out what somebody else is doing and why, to read their mind in a sense, even for a complex action like this that you've never seen before. Think about it. Watch this kid. These kids are just 1.5. If we could build robots with this kind of intelligence, with this skill and helpfulness around the house, with this kind of common sense, that would be amazing. So to do this, we've had to invent new kinds of AI programming languages known as probabilistic programs. Okay? These build on, but go far beyond the deep learning that's driving today's AI. And they allow us to bring together the best insights from multiple eras of the field, ideas that may not have a simple home in today's neural networks, all into a unified framework. So this means, for example, symbolic languages for representing and reasoning with abstract knowledge, or probabilistic inference for reasoning about cause and effect from sparse, uncertain data. Probabilistic programs may be what you're going to be hearing about in the next few years, if you haven't yet. Just to give an example from research, just in the last year, in 2018, we and many of our collaborators have used these tools to give that kind of intuitive physics to robots, to allow robots to stack up blocks and even play the game Jenga, to be able to imagine how to use new tools, even ones they've never seen before, to plan complex actions, to make sushi, or at least the rice, to pour ice water, and even to learn to walk. The next step, the next challenge, is model learning. How could a child or a robot build an intuitive physics model for themselves? Learning these probabilistic programs means that your learning algorithm has to be a learning program, an algorithm that writes algorithms. It's the child as coder. This is a much harder form of learning than in today's neural networks, but children do it, so machines can too. Now, we've made a small step towards this with a system that can learn new programs that can capture simple visual concepts, such as a new tool or a new handwritten character. So look at these here. You can learn thousands of new characters in new alphabets from just a single example each. You don't need 1,000 examples to learn a single new concept, like today's deep learning systems. Now, our Bayesian program learning system can learn like you do. It uses probabilistic programs to model the causal processes that put ink on the page, programs for writing and action and drawing. And then it runs these programs backwards to learn the program most likely to have produced the character you see. This lets us generalize new concepts from a single example and even pass a simple kind of Turing test like this. We can show a new concept to both humans and our machines and ask them to draw new instances, to imagine new examples. Now, can you tell which are the people's and which are the machines' drawings before I showed you? Try here. See if you can. My bet is that most of you couldn't, okay? So we're passing this very simple Turing test. It's a small step, but it does scale. This idea lets us learn programs that can describe the shape of a chair, that can answer questions about pictures, and that can even learn a new video game 1,000 times faster than today's deep reinforcement learning systems, and almost as fast as a person can. Will this be the idea that finally delivers on AI's oldest dream to build machines that learn like children? Probably not yet, but it may be the next small step. It may be the next form of deeper learning, so stay tuned. Looking ahead, once we've reached this first moonshot stage in our program here, the 18-month-old stage of common sense, stage 2 is to learn the most important thing that every child learns between age 1.5 and 3, and that's language. And then stage 3 is using language to learn everything else, to access the full sweep of human knowledge that builds culturally across generations and across societies, and that puts you in a position to contribute new knowledge yourself. If we could build AI like this would be AI that lives in a human world, that humans could talk to, teach, and trust the way we've always done with each other, even with people that we're just meeting for the first time. This could be AI that makes us actually truly smarter and better off. Thanks.
Good afternoon. So in life, there are some very significant moments, birth of a child, getting married. So in the life of institutions, there aren't too many such moments. I have been 34 years at MIT, and I believe today is such a moment. So Steve and Raphael, thank you. So I would like to talk to you about interpretable AI, and to motivate, suppose you consider a driverless car, and this driverless car is involved in an accident with loss of life. Who is at fault? The driver, the passenger, or the algorithm? And most importantly, can society tolerate not understanding this question? For another question similar, closer to us, let's suppose you have a student who is not selected for freshman admission, even though he might be the valedictorian of his high school. Is it an adequate response for the algorithm to say that the algorithm made the admission, this decision? I suspect not. So in my view, and perhaps in the view of others, interpretability matters. However, existing methods achieve either high-quality performance or interpretability, but not both. For example, neural networks that we have heard lots about, but other methods that have exotic names like random forest and boosted methods have high-quality performance, but low interpretability. More classical methods like regression, developed 200 years ago, and classification regression trees have high interpretability, but not as high-quality performance. In my group, we aspire and to some degree we succeeded, on developing new methods that have both characteristics, both interpretability and high-quality performance. One of my heroes, Leo Breiman, who passed away about 13 years ago, he developed one of the most interpretable methods, classification regression trees, CART for short. And he commented that on interpretability, trees rate an A+. However, on performance, they were not as strong. So we developed in my group some methods that are like trees, except we use the tremendous progress that my field optimization has made that allows both interpretability and performance. And in addition, allows to partition the space into, let's say, in a classification setting, into regions in which we can make a decision, classify appropriately. Just to illustrate an example, this is actually an example developed with Dana-Farber researchers on predicting the mortality for a patient taking chemotherapy. I have a personal connection to this application. My father was diagnosed about 12 years ago with gastric cancer, and until the very end, the doctors with very good intentions were prescribing chemotherapy, even though it was very clear to me, at least, that the end was very near. So using these new methods, we have developed algorithms that are state-of-the-art in terms of performance, that predict mortality, but most importantly, they are interpretable. And at least in my experience in the last decade or so with medical doctors, interpretability is a must. That is, if you say to a patient, stop chemotherapy, a natural question is, why do we believe that? And the algorithm, if you follow the algorithm, it says, because that at least the doctor understands, certain enzymes are elevated, the change of the weight is elevated, you can explain the reasons. And that's the claim, just to illustrate, regarding the combination of predictability and performance. So on the horizontal axis is the depth of the tree, the number of questions we ask, and on the vertical axis is the accuracy of the method. The blue, this is like the tree we have seen for chemotherapy, has about the same performance, slightly better in fact, than a state-of-the-art method called random forest. And the green, this is a tree similar to that, except that instead of asking one question, we ask multiple questions at a time, has similar performance with another state-of-the-art method, boosted trees. So this enables the application of these methods for assessing mortality, morbidity, and many other questions in medicine. This is an application we developed with Mass General Hospital, currently at use at the trauma department there, in which an incoming patient in the emergency department, before any surgery, but just on data, we make predictions about mortality, specific morbidities, or any morbidity in ways that are understandable. They are delivered like the application on the right. And as I participate in discussions with doctors in the morning rounds, I have seen that it has changed the dialogue. It discovers things that humans typically don't fully understand or expect, because many human doctors have, let's say, thousands, maybe 2,000 experiences in their lives. This is based on about 1 million experiences from hospitals all over the country. Clearly, the sheer volume of data, in this case, beats the human experience. Of course, this is not really only to surgery. In many other applications, we have seen similar results for cancer, cardiovascular disease, type 2 diabetes, liver, and kidney transplantations. On pharmaceutical research, clinical trials typically analyze the mean of the treatment effect. However, subgroups might exhibit a very different response. So these trees that we have developed, optimal trees, we have applied it, and they produce very interpretable subgroups. And in this case, identifying subgroups of exceptional responders could guide the design and inclusion criteria could find new signals in failed trials, identify opportunities to relabel existing drugs. In summary, the message I would like you to remember, and I believe other speakers have spoken, is interpretability matters. And relative to our discussions on ethics, I would say interpretability helps the ethics discussion because at least we understand what the algorithm is doing. It's not just a black box. On that note, thank you.
Welcome, everyone. I'm Aleksander Mądry, and I will talk about AI. Surprise, surprise. But actually, what I want to talk about is the aspect of AI that I think we need to get right to make sure this is actually a successful technology. Okay? So I guess it's fair to say by now that we all are very excited about what AI seems to be able to do. Like, things that we thought are impossible to do merely 10 years ago now seem to be completely within our grasp. And this is exciting. So we are thinking of all the ways in which AI can change the way we work, the way we travel, the way we play. So, I think we can just say we are all ready for AI. We are all excited about this. I am excited. But as excited as I am, I can't stop to be also worried. Okay? Because I think that there is a question that we should be asking ourselves, a question that actually drives most of my recent research. And this question is, even if we, as much as we are ready for AI, is AI ready for us? What do I mean by that? Let me demonstrate. So what you see on the right is a beautiful pig. To us, human, it is a pig, and the state-of-the-art classifier will view it as a pig as well. So far, so good. What's interesting here? Well, it gets interesting if I add to this image a little bit of a carefully chosen noise. What I will get is the picture on the right, which again, to us looks like a beautiful piggy. However, to the state-of-the-art classifier, this is actually an airplane. So there are two lessons here. The first lesson is, if you ever doubted, AI is a magical technology. It can make pigs fly. That's important. The second thing is, that's not what you would expect to happen. So what's going on? Well, your first reaction might be, is this for real? Because indeed, I told you that the noise I needed to add has to be very carefully chosen, and maybe in the real world, I can't have fine-grained enough control over what the machine sees to really trigger it. And that's actually what many people initially thought, until a bunch of MIT undergrad proved them wrong. So what they did, they 3D printed a turtle that looks like a turtle to us, but essentially it classifies as a rifle from all angles and zooms. Okay? So if you ever doubted this so-called adversarial perturbation is a real thing, so, well, should we worry about that? And the answer is yes. And why? Well, many reasons. The first and the most obvious one is security context. If I can make your system see something different than I see, that's how many security breaches start. Okay, so one of the promising uses of this technology could be in face recognition. And here we see a state-of-the-art face recognition system that recognizes correctly the person on the picture, despite having these funny glasses. However, when this person puts on this even more funny glasses on, something magical happens. The system believes this is a completely different person. Think of the implications. But yeah, this is security, but what about safety? Sometimes we don't really believe there are some bad guys who want to get us, but still there are systems like that in which we really want to be sure that there is no inputs that cause some undesirable behavior. And true enough, this system has a very undesirable behavior if you just perturb the picture that you have in the right way. Okay? So this is about security and safety. So it's about getting the correct decision, getting the decision right. But sometimes, it's not only about getting the correct decision. It's also important about getting this correct decision for the right reasons. So, for instance, one of the promising applications of AI was to use it in hiring, to make decisions about who to hire and who to not hire. And the idea was that, well, this should be purely data-driven, so the outcomes will clearly be impartial and optimal. Okay, so that was the dream. what happened in reality? Well, what happened in reality is that using these solutions actually reinforced all the biases and all the inequities that we wanted to avoid in the first place. And my most amusing example here is a resume screening tool that came to the conclusion that the two most important factors predicting job performance is being named Jared and playing lacrosse in high school. So yeah, so things are not great, and it's definitely we should be careful about that. But one more aspect I want to talk about is about the who will this kind of AI benefit, at least the AI technology that we have now. So think about what do we need now to deploy an AI solution. We need a lot of data, we need a lot of compute. Also, we need an education that is actually quite hard to get. So MIT and other universities are trying what we can, but still there's not that many people who have the right training to use ML. So is this something really that an average man can use, understand, and apply? I don't think so. So I guess the conclusion here is that AI technology that we have now, it has to change, it has to evolve. So on one hand, it has to be secure. It should not be it should be tamper resistant. It should not be something that is the weakest link in our current system from the security point of view. It should be reliable, so we can actually confidently deploy it in the context where human lives matter. It also should be equitable. It should be mindful of the societal impact of the decision it makes and make sure that it's consistent with our values. Finally, it needs to be accessible. So essentially, even people without the specific training and this hard-to-get resources can actually fully take advantage of this. So the way I like to phrase it is that essentially what we need is we need AI to zero, which means we need to look at the AI 1.0 that we have now, the proof of concept AI, and think about all the ways, all these aspects over here, and figure out how to fix them, and only then have the AI to zero that we actually can deploy. So essentially, trying to come up with this AI to zero is what my group spends most of its time on, and there are two lessons that we have so far. So one lesson is that actually many people think of getting one of these goals in isolation, but actually it turns out that if you try to go for all four of them, you actually have some very nice synergies that you can and you should take advantage of. The second lesson is that actually, even if your goal are just this, achieving these four properties, you might end up with models that are also better from the point of view of more traditional properties. In particular, the models that you get to be robust, they actually also turn out to come up with better representation of the data. So let me demonstrate. So what you see on the left is just a picture of a dog that is correctly classified as a dog. So far, so good. But it's sometimes useful to look under the hood and just see why did the model decide this to call it a dog. And essentially, one natural way to do it is to create a heat map when you look at every pixel and you see how much influence this particular pixel had on the final decision. So if you do it to a standard model, to the AI 1.0 model, you will get a heat map like this, which is only mildly informative. However, if you do it to a robust model, you will get things like that, where essentially suddenly what was driving the decision of the model seems to be much more compatible with what we humans would think as important. Okay? So the goal is AI to zero, and this is, of course, a quest that goes beyond any single research group. You need to get expertise from many different domains that also transcend CS. So, in particular, College of Computing, I think, is poised greatly poised to exactly tackle this challenge. So, there is many of my colleagues here that think about these questions and share this vision. These are just some of them that I talked to so far, but there are many, many more. But this is more than just about faculty thinking about this stuff. I think the most important mission here is to educate the next generation of engineers and researchers that understand these issues and know how to deal with them. And that's what we are doing at MIT as well. I believe that this is my group, and I believe that in my group there will be many of the future leaders in this field, but there will be many, many more. And essentially, the goal here is to get AI that actually is ready for real-world deployment, the AI that's actually human-ready. Thank you.